over linear regression with single variable and multivariable using Python. So initially, let's get started with the dataset that we will use in this video and in few of the following videos. So we will see some dataset or a dataset that or a datasets package that already included in Python. So we will learn how to install it, and we will see a few packages that already exist in Python that we also need to install for plotting our results and see how to plot even the dataset that's given. In addition to that, we will learn about a machine learning package that's called SKLearn, and we will use it for splitting our data into train and test dataset. Let's get started and start with installing dataset package. So there is a dataset package that I found online. It's called Vega datasets. You need to install it just as we installed packages in the previous videos. Please go to Anaconda, the terminal, and type pip install Vega datasets. And for creating plots, we have also two packages that we need to install. The first one is matplotlib, and the second one is Seaborn. Please go ahead and install them before you proceed in this video. Then we need to install SKLearn. SKLearn is another package that includes machine learning methods that we will use in this video and the following videos. So the datasets or the package of datasets that we have in here, Vega datasets, it's available, and some information about it are available in these two links. Please feel free to go ahead and just read these datasets and some information about them, and go over the available datasets and what are the variables of each dataset. In the first line, I like to import all of the packages that I need to use within this tutorial at the beginning of every Jupyter notebook, or of every notebook that we use. So I started by importing pandas. I imported NumPy. I imported matplotlib. From matplotlib, I imported pyplot as PLT, and I also, from Seaborn, I imported Seaborn instance in case we want to plot fancy plots with the Seaborn. From sklearn dot model selection, I imported train test split. So this train test split is a method or a function that we can use to divide our data into some sort of ratios. For instance, if I provide the data, my data, as well as the labels to this function, and I specify I would like to divide the dataset into 90% for training and 10% for testing, or 80% for training and 20% for testing, and this package will split them for me as well as the labels. Then we will see from sklearn as well, there is linear model, and I imported linear regression from linear model. From sklearn also, I imported metrics. We will not talk about metrics in this video, but we will talk about it later on during this series of videos. Matplotlib inline. So this line is just to display our plots in line within our Jupyter notebook as an HTML plot. So if I omit this line, most likely Jupyter notebook will create the plots that we create as a pop-up messages, or save them as, I can save them later on as PDF. So therefore, since I would like to see my plots on the screen, see them within my Jupyter notebook, I imported, or I provided this directive to the compiler so it can display them inline. So let's get started and compile or run this cell and move to the next one. So let's import the data from Vega datasets and list the datasets by using data.list datasets, and this will list all available datasets for us within this package. So you can see in here we have a few datasets that are available, a handful of them, around, like, I don't know how many, maybe let's see how many datasets we have. So you can see that by just printing the length of this list. So we can go with print, and it's a list. So we can just view the length of this list and see how many datasets we have. So you see we have 70 different datasets within this dataset. So I would like to use a weather dataset that I'm familiar with. It's Seattle weather. So you see in here, Seattle weather is Seattle-weather. So whatever you call it or you want to retrieve its contents, you replace this dash or this hyphen by underscore. So data.seattle-weather, Seattle_weather, and then let's see the description of this data. So the data will be retrieved in the form of pandas. So whenever I say I type dataset.describe, it will show me a quick description for the variables that I have in this dataset. So the numerical data within this dataset is we have precipitation, we have temp max, temp min, and wind. In fact, it's not the only variables within this dataset. So let's see what other variables we have in this dataset by displaying just the head, the first 5 elements within this dataset. So we see there is a date, there is a precipitation, where there is a temp max, temp min, wind, and weather. So this date is the date where the data has been recorded at, and we have weather is a categorical variable. So we call this as categorical variable because it's a numerical, this variable possible values are values that we cannot apply mathematics and logical calculations on. For instance, the weather in here is a description, drizzle, rain. Let's see what others we have. So I can display how many unique entries or the unique entries within this variable values by saying the dataset dot weather, which is the variable name. Then you can just type unique, and this will call the unique values and just keep the unique values of this variable. So we have drizzle, we have rain, sun, snow, fog, and so on. So this weather is a categorical variable, and it's a the categorical variable is a variable that you cannot apply math on it. So for instance, I cannot add 5 to all of this weather. It's just a string, or I cannot multiply it by 20. I cannot find the standard deviation for this weather. I cannot find, for instance, compare it to greater than or equal to 5 or less than 100, because the values in here are just an actual string. So therefore, this is what we call as categorical variable. So we have a categorical variable in here, the weather, and we have 4 other variables. So in this example, we'll try to predict the precipitation using the 4 parameters or the 4 variables, the 4 features that we see for each date. Now let's look at the size of our dataset by calling the dataset.shape, and now you see we have 6 different columns, 6 different variables, and we have 1461 different rows or data points. Let's plot part of this data, and let's plot the temp, for instance, the temp max, and see what's the general distribution of our data set. So to do that, I called plot PLT. If we go all the way up, you will see that PLT is part of matplotlib pyplot. So I go with PLT dot figure. This will create a figure for us, and the figure size, how many columns and rows we would like to make this column to be. So this is the width and the height of the plot, and then the tight layout will make our plot layout tight, and then Seaborn instance. If you go all the way up, you will see we call this from Seaborn package, Seaborn instance dot display plot or dist plot, and we provide the variable or the pandas variable that we would like to plot. Now when I hit run, it will display the temp as an x-axis, and the y-axis will be the possible values of our dataset. As you can see in here, this is our dataset, and it's centered around like maybe 15, the mean of this dataset. And let's see the max, the min. So that was the max, and this is the min. Similarly, the min is around like 7, maybe 8, the mean of our data set. And let's display also the precipitation, and as you see, our precipitation is almost, the mean is around 0, and the data is not equally distributed. So therefore, that might impact our like our data is more biased. Our precipitation between 0 and 1. We have some data distributed like maybe above 5, but it's very, very small. So most of our data is between 0 and 1, as you see in here, or less than between 0 and 5. Okay, so the first step that we will do, or the first example that we would like to go with, is again, predict the precipitation given a temperature minimum or maximum. So what I'm planning to do in here, just use a single or one variant or one variable linear regression, and the input will be the temperature minimum, and the predicted value will be, or the label will be, the precipitation. So we started by dividing our data. So I initially started by taking our data set. So remember, our data set includes around 1400 data points, 1400, I think 60 something. Let's go up and look at it again. So our data includes 1461. 1461 examples, we retrieved the temperature minimum, which we named it as x because it's the variable that we will use, and then I took these values and took the values, and dot values will convert our dataset into, or this pandas dataset into, a NumPy array. Then y, I retrieved the precipitation. I converted the precipitation values to a NumPy array and reshaped it to be a one-dimensional vector, and I saved it in y. Let's compile this and see what will be the value of y. Again, as I said, it's a NumPy array. We can look at the shape of it, and it's 1461, which is the labels or number of precipitations, and the values all are numerical values. So let's just comment it, real values, sorry. And x similarly will be numerical values. We can just look at the shape, and the shape will be 1461 by 1 because it's just a single column. So let's just make it as a comment to reduce the clutter, and we can delete them, but I'll just keep them so I can upload this file for you guys so you can have a look at it. Okay, so let's divide our data. I like to divide the data like maybe 20% for training and 80% for training and 20% for testing. I highly encourage, if you have a data set or a model that you are, for instance, creating for a production, just to make 80% for train, 10% for validation, and 10% other for testing. But just for the sake of simplicity, in this example, I divided our data in here into 80% for train and 20% for test. So to do this, you can just, for instance, shuffle your data, randomly permutate all of the indices, and just retrieve the data and divide it into 10 and 20%. However, to make it simpler, we used a train test split method, and this method is provided from SKLearn. And I provided the following parameters. The first one is the dataset that I would like to split. It's a NumPy array. The second part is the labels that we would like to split, which is y. And then the test size. The test size is how much is the size that you would like to dedicate for your testing, and the rest will be for training. In this case, it's 20% or 0.2, and this will create 20% for testing. The returned values will be xtrain, which is the training dataset, will be saved in xtrain, the train split of the dataset. Then xtest, the actual features for testing, will be saved in xtrain, which is 20%, and the actual features for training will be saved in xtrain. Ytrain will be the labels for the training dataset, which is the labels of the 80% data that we have in xtrain, and ytest will be the labels for the ytest dataset. Now I tried just to display the sizes of the data before and after I've done the split. As you see in here, initially the dataset is 1461. 80% of this data is around 1168, and the test data points are 293 data points. and this matches training and testing. That's just the same. And since this is a single feature, we have it as 1168 by 1, and the label is all the time will be one single value. Now remember, we talked about normalizing the data, and we have seen how to scale the data or normalize it in multiple methods. I like to normalize my data initially by subtracting the mean and dividing by the standard deviation of the data set. So we started by calculating initially, finding the maximum and minimum for the train and test data set, just to have a feeling about how the data is. Then I calculated the mean and standard deviation for the training dataset. I saved them in two variables, and later on I took the X train, I subtracted that from the train mean, which is the train mean that I calculated previously, and then I divided all data points by the standard deviation of the training dataset. Then, as I mentioned in a previous video, I used the same training dataset parameters to normalize the testing dataset. So the testing dataset never been used for normalization, like for calculating normalization parameters. As you see in here, I calculated the mean and the standard deviation after I split the data. So therefore, the result will be a normalized training dataset. I just added as a sort of postfix to the variable name underscore norm, just to indicate this is a normalized version of the dataset. Then I printed, this will print 20 stars, and these stars just to separate the maximum from the minimum, so I can tell the maximum before and the minimum before I normalized for both testing and training, and the normalization or the maximum and minimum after I applied the normalization. So you see in here, after I normalize the data or rescale the data, so now this will remove the mean and the standard deviation of our data, and the maximum for training was before the training, it was before the normalization, sorry, it was 18.3, and the minimum was minus 7.1. Similarly, for the test dataset, it was 17.8, and the minimum minus 3.9. Now, after I scaled the data, it's between 2 and 3. And this is the training, and the testing is around 1.8 up to negative 2.3. So the data now is rescaled, it's pre-processed and normalized, and I did not see any not available data or missing data points, so therefore I did not apply anything about not available or null. I highly encourage checking that ahead of time and get used to the habit of checking the not available and is null. If you do not recall how to do that, please go back to the previous video and watch how we identified not available data and how we filled them into either. You can fill them either in the mean of that variable, or just exclude them, or fill them with zeros. There are multiple methods in machine learning and data mining that you can use for imputing or recovering or filling the missing data points, and it's out of this video's scope. We'll talk about them maybe later on. Now, from SKLearn, now I would like to create a linear regression with one variable, and it fit. The linear regression will have two parameters and fit or one coefficient and multiple features. One feature, we have one feature now, and then calculate them to use them for creating a model that we will use for predicting unseen data points. To create a linear regression, it's easy, fairly easy. So we used linear regression object or linear regression function from SKLearn. If you go all the way up, you will be able to see that we imported linear regression from sklearn.linear model. After I created the object, I can use the function. So I saved that in regressor, and then I can use regressor.fit. I provide the training dataset, the actual features, as well as the second parameter will be the labels of the dataset. And all of that, the fitted model will be saved in this regressor. Now you can see trained very fast, and now you can just look at some of the variables such as the coefficients. You can look at the number of features. So we have only one feature that we fed to this regression model, and the next step is to use the trained model to predict the actual or the values for the unseen test dataset, which is the 20% dataset that we held just for the purpose of testing. Now, since this is a regression, it will provide you with real numbers, so they are continuous numbers, in fact, and I would like to save them in Y predict, so we can compare them later on against the ground truth. Now, when you compile, now if you look within a Y pred, so let's just look at the Y underscore pred, and this will be numerical values which are sort of the prediction of the test dataset. So how much is the precipitation that we have seen for our dataset? So I'll comment it out, and as you can see that the values are almost similar. That means the model is not in a good shape. We may have to play with the parameters or try to add more features to make it more accurate, and instead of using just linear, so that indicates that there is no linear relationship between our variables and as well as our classes. So therefore, linear regression might not be the best option for solving this problem. But we will proceed with linear regression just for the sake of this example. Now, we will take the actual values as well as the predicted values and just place them in a data frame, in a pandas data frame, so we can see them side by side. So what I've done in here, I created a new data frame, pandas data frame, and I created the one column. I added the header of the column. I named it as actual. Then the values of that column will be y underscore test, which is the y test, which are the values that we have created when we split the data, dot flatten, just to make it as one vector, and this will create one column. I created the second column, and the title of that column or the name of that column is predicted, and it will have the y predict, which are a numpy array that contains the predicted values for the tested or evaluated features. Now we displayed the new data frame in this line, and as you can see, the actual sometimes is 0, and these are the actuals. This is 8.4, this is 0.0, and so on, and the predicted value is in the second column. Now let's try to plot the predicted versus the actuals side by side, each data point, and just see how we performed. So what I've done in here, as you see in here, we have 292 different values for testing. So like if I try to display them in one plot, that might take like a wider screen. So therefore I would like to just show the first few of them, like maybe the first 15 or first 20. Let's just show the first 50 elements or the first 50 data points comparing the actual versus the predicted, and then show them in a figure. And I would like to show the major as green and the minor as black. These are in the grid, the actual lines, and let's show the comparison of the data frame. So you can see in here we have the actual prediction, or the actual precipitation is in blue, and the predicted values are in orange, and we are comparing them. As you can see, sometimes they are zeros, and our forecast, or our prediction is showing, our linear regression prediction is showing different values. So we can see the difference between the predicted values as well as the actuals, at least for the first 50 data points. Now let's try to plot how we fit, or the line that we fit with on our data. So you see these gray lines. We are plotting the red line is the predicted, or so the ground truth, which is plot the x test and y prediction in red. So these are the actuals, and so we are plotting the test versus the predicted, and we are plotting also the x test, which is the actual values, versus the predicted or the ground truth. So the ground truth are the given labels for the data. So we are creating a scatter plot as well as a line plot for the predicted values. As you can see in here, we have a lot of zeros. The gray dots are the ground truth, the given values. So we have a lot of zeros and very small number of non-zero values. So therefore, our model includes bias toward the zeros, so therefore it did not perform as we expected. Now, there is a measure that we'll talk about later on, which is called mean squared error. Mean squared error, it's in fact something similar if you remember in the gradient descent, when we tried to find the distance between the actual value, between the actuals or the ground truth and the predicted values. So we subtracted the predicted values from the actuals, and then we take the square of that and divide by the number of entries, and this will provide us with a mean squared error. So the mean squared error is available in matrix, and you can call it by calling matrix dot mean squared error and provide the tested versus the predicted values, and then save that as an indication. The higher the mean squared error, the worse the model is. The lower or the smaller the mean squared error, the closer to zero, that means your values are much closer, or your model fits your data very well. Let's see where we got this matrix from. We got it from SKLearn, and you can see we have mean squared error, we have MAPE, mean absolute error, we have mean squared error. So we have multiple types of matrix that we can use for linear regression and comparing actuals versus predicted values. I just used mean squared error in here for there's mean root error. There are multiple types of metrics that you can look them up and see which or what values or what metrics you can use and what makes sense to your application. Depends on the application, we select a matrix. So now in the previous example, we have seen all of what we have seen. It was just single variable. We used it to predict the precipitation or another variable within our dataset. Now let's try to incorporate more variables. Let's add more features within our data. So let's look at the data again so we can remember what features or what variables we have. We said we have 6 features, and the date we will just put it aside, we will not use it. So we have precipitation, which is the label that we will use. Let's just say this is Y. We have temp max, temp min, we have the wind, we have the weather. Now, we have seen that the weather has 5 different unique values, and it's of type categorical. So I would like to change the representation. Instead of using this categorical variable, I would like to switch it to be more of a numerical value. To be a numerical value, there are multiple ways of converting or representing or encoding categorical variable into an actual numerical value that can be used for calculations and to fit them on a model. So I will use one very simple method of converting this categorical variable into a numerical or corresponding numbers. It's not the best method, but for simplicity, I will just go with it. And the method says, just take the unique values, give them numbers. For instance, drizzle will be 1, rain will be 2, sun will be 3, 4 for snow, and 5 will be for fog. So, and this representation or encoding is available within pandas, and I will save it in a new variable. So I will save the new representation or the new encoding dataset weather code. I will name the variable or the column as weather code, and to convert our categorical variable into this encoding, I will use the dataset name dot the variable name, and then I would like to make sure it's of type category. As you see in here, it was of type object, so now I convert it to category, then dot cat, and finally dot codes, and this will code all of your variables automatically for you. One of the best methods for encoding your variables is called one-hot encoding. We will talk about one-hot encoding later on, but it's out of this class scope or out of this video scope, so therefore we will just go with a very simple categorical encoding method, which is just an integer values. Now, after we added this variable, let's just display our values. As you see, it starts from 0. Sorry, I said it's 1. So this will be 0, 1, 2, 3, 4. So you can see in here, this is 0, rain is 2, and so on. So it encoded all of our categorical variables into a numerical value so we can use them in calculation. Now, my training data set, I will do something similar to what I have done before in a single variable. So in multi-variables, I would like to use the variables of temp max, temp min, wind, and weather code. So these are 4 variables that I will integrate within my model, and the precipitation will be the label for this experiment. So I selected the 4 variables. So you can select that from this pandas data frame by typing the data frame name between double square brackets. You type just the titles or the column names that you want to include between single quotes and separated by comma. Dot values will convert that into a NumPy array. I've done the same for the labels, so I have now my training data set is within X and the labels are in Y. Compile it and run it. Let's just show the same stat or the same information of the shape. So the shape is the same except that the X now is with 4 columns. If you remember in the previous example, it was just 1 column because it was linear regression with 1 variable. Similarly, we just divided the data into 20% for testing and 80% for training. Let's normalize our data. Now be careful, when we normalize our data, we added axis equals 0 to the mean and standard deviation as well as the min and max, because when I normalize the data, I normalize it by column. So I will take for instance, I will not normalize the labels. What I will normalize, I will normalize the temp max, the temp min, wind, and weather code. So what I will do, I will take the mean for each column and just set it aside, and the standard deviation of each column. Then I will take the column, for instance, the temp max, and then subtract each value from the mean of the temp max values, and then divide by the standard deviation of the temp max. And I will repeat the same for temp min, the same for the wind, and finally for the weather. And this is the normalization or scaling to make sure that we remove the variation from our data and make our gradient descent converge faster and avoid falling into a local optima that does not provide a global solution. So therefore, to do that, I made sure that I use axis equals to 0. If you would like to verify that we are correct in here, so I'll just add a simple a blank cell in here, and so our data is already labeled, so let's just add it after. And we have xtrain. If I use xtrain max, for instance, this will provide me the maximum across all of the 4 columns. But if I provide axis equals 0, this will provide me the maximum value in each column. As you can see, we have 4 columns, so the maximum value of each column is displayed separately. So we have done the same for max and min, and as you see, the maximum and the minimum for each value before normalization. I calculated the mean for training and the standard deviation for training using axis as well, axis equals 0. And then when I subtracted and divided by standard deviation, subtracted the mean and divided by standard deviation, since I have 4 columns, I will have 4 means and 4 standard deviations, and this will do the subtraction and division with the associated mean and standard deviation for each variable or each column. Now our data is normalized and scaled into the proper, like you can see, it's around between 2 up to -3 in most of them. Now let's split our data. I think we already split the data before, so yeah, so this is a split of our data. We already split the data into, so I do not need this line. And after we split the data, we created linear regression now, and this linear regression will fit the train as well as the labels. But keep in mind the training now is 4 columns. They are not as in the previous example. So we have 4 variables. Now let's try to get the coefficients as well as a coefficient for each x and how much is the value for these coefficients and create them into a data frame. So you can see in here there is a temp min with a coefficient, a temp max and wind, weather code and so on. So we have coefficient for each of these variables, so of each of these features, what we called as x's within our lecture. Now the model that we created in here, it was saved in Regression again, and I would like to predict the x test. So you can predict the x test. Now after I predicted the x test, I would like to go and compare the actuals against the predicted values and just display the first 50 values. And you can see now the predicted values are different than what we have seen previously. So in the previous linear model with one variable, the values were very, very close. Now the the values are a bit more different. Now let's just display the first 50 using a bar chart, and you see within this bar chart now we have some values are much closer. This is different far, and this is much closer than the previous scenario. Now we can calculate the mean squared error. Let's just go and get the same equation that we used from previously and see what's the mean squared error. Again, it looks like the relationship is not linear, so therefore the results are not as good as we are hoping for. So the mean squared error in here is 22.98, which is around 1 point better than using just single variable. So this is the end of our this video, and thank you.